So now let's talk a little bit about inverse functions. In order to define what an inverse function is, we need some additional definitions for some properties of functions. The first one is one-to-one. Okay? So a function f of x is one-to-one if it never takes on the same y value twice. Mathematically, I can write this as f of x1 is not equal to f of x2 as long as x1 is not equal to x2. All right, well, that's just sort of a random thing. But the idea is, let me give you some examples. All right, something like this is one-to-one because for every y, I'm only going to get that y one time. There's one x. Whereas if I have something like this, there's my favorite friend, y equals x squared again, I've got two separate x's for that particular y, right? And of course you know why, right? Because you square it kills a negative. So if I've got y equals x squared here, let's say this is 2 and this is negative 2, we can see it fails this definition because f of 2 is f of negative 2, right? They're both 4, but of course 2 is not equal to negative 2. Okay? If I look at something, let me be a little bit more specific then. Let's take y equals x cubed. So x squared is not one-to-one. It's always good to have an actual conclusion written on the board, right? Let's do y equals x cubed. Let's put it up there. What we can do is we can actually prove this statement very easily if we're just going to do if f of x1 equals f of x2, then, here we'll call it f of x, right? I should have written it this way. Sorry, guys. So I have got x1 cubed equals x2 cubed. I can take the cube root of both sides, right? Let me just write that as a separate step because it's going to get too messy. x1 cubed to the 1/3 is x2 cubed to the 1/3. These guys cancel, and that gives me x1 equals x2. So the contrapositive of this statement, if you prefer to remember it that way, is if f of x1 equals f of x2, then x1 equals x2. So this is a little bit easier to prove when it's equals instead of non-equals. I'm not going to ask you to be proving these things. Why does this fail for this x squared business? I can kind of do the same series of steps, but when I take the square root, you remember I have to think about the positive and negative square root. So I can write down this stuff, but it's not going to work out. Luckily for our cases, we don't really have to worry about proving any of these that much. It's pretty much going to be, you can look at the graph, and I'm sure you guys have already heard of the horizontal line test, so I will remind you of the horizontal line test. The horizontal line test is exactly what I did when I put that 2 thing in there through, right? So my horizontal line test, obviously, if a function has a y value for 2 different x values, a horizontal line that goes through that y value is going to hit the function more than once. So what we have here is basically that statement in a test form. If every horizontal line hits the function only once, then the function is one-to-one. So this is a very easy visual test. It's kind of nice. The vertical line test tells you whether your graph is a function. Your horizontal line test can then tell you if that graph is a one-to-one function. And in fact, you'll see a little bit later why these are so nicely related. All right, so that's one-to-one. Now we have another property of functions called onto. So for onto, we have to be a little bit careful. I want to be clear on this. Remember, we talked a little bit about codomain versus range. So this is where onto comes into play. This is where codomain and range come into play. So if I take a function, domain is A, and say codomain is B, but maybe it's not the range, right? There we go. So this is the definition of onto. So the function f from A to B is onto the set B if every b, little b, in the set B has a corresponding A in big A, so that f of little a is little b. Right, this is sort of like a fancy way of saying that the codomain is actually the range. And I think this is why your book doesn't make a big deal out of it. So I'm also not going to make a big deal out of it. Fine. Especially in Calc 1, it really doesn't make a difference. But so just know that there are times when we write this kind of function notation using something which is a bigger set than the range, like we talked about before. And if you want to talk about something being invertible, like we're going to talk about in a minute, you can't have it that way. It has to be defined properly so that your B is actually the range. We're just going to work that into our definition, though, of invertibility so that we don't have to fuss too much about it. I just wanted you to know about the issue so that later on when it appears, you're like, I mean later like in 2 semesters, 3 semesters, whatever, like not later on in this class. Because not all of you will ever really care about this. So it's fine. Anyhow, so that's the idea. But to give you an example, if I write, again, let me use my friend x squared, right? I'm going to write f from R to R. Okay? Well, there's my picture. This is not one-to-one, obviously, we just said that. It's also not onto. Why? Because here's R, my codomain, that's this entire y-axis, and there's no points down here, right? All the points are up here. It's the wrong thing, okay? So if I do it this way, this is not an onto function. So this is not onto R, right? Because I only have the positives or the non-negatives. However, if I switched it, then it's onto that set, the set from 0 to infinity. So it's just a question of sets, right? Making sure everything is defined right. And for our purposes, we won't really be using this definition, but I just wanted it to be out there. Okay, so I am next going to define the inverse function. And then in the next video, we will do some examples with inverse functions. Okay, so what do I mean by an inverse function? Right, we already saw some examples here. One taking the cube root, taking the square root. Going from one set to the other is something that we know. Now I want to go back. Okay, so just visually speaking, let's take f, function f, from domain A to range B. Right, so f has domain A and range B. Okay, I'm just going to draw a picture. Okay, this picture here, 1, 2, 3, go to A, B, C. Or let's put all numbers, 4, 5, 6, right? So if I go this way, I can always go back the other way. Right? That's not a big deal. And that's exactly the idea of the inverse, is that I want to define going back the other way. In order to do that, though, I need to make sure that I can define it properly. So, how do we define this? Let me write it down. Let f be a one-to-one function. That's what we need to define it properly. We need it to be a function, and we need to be one-to-one. And we need it to go from the domain to the range. Okay, then the inverse function and our notation is f with a minus 1 of s, f with a minus 1 of x, is the function defined as f inverse of y equals x if and only if f of x equals y. So we're literally just reversing the process. Okay? And this has to be true, though, for every y in B. So in my picture that I drew here, you can see that f of 1 equals 4. So if I go backwards, I would write f inverse of 4 equals 1. I'm just going the other way. All right? So there's, and if you ask me what f inverse of 6 is, well, from 3 gets sent to 6, so 6 gets sent back to 3. So that's really all it is. Of course, it's very easy with this diagram. Maybe with some functions that are more complicated, there are some more interesting things to look at. So I will do some examples in the next video, but before I finish, I do want to mention a crucial point, just so not to get confused. This notation with the minus 1, right? So it's not an exponent, right? You're often used to seeing something like x to the minus 1, and we write that as 1 over x. Fine, but for a function, this doesn't mean that. So f to the minus 1 of x is not 1 over f of x, right? It is the notation for the inverse. All right, so don't make that error. If I do want to write 1 over f of x and I want to use a negative exponent, I would write it like this. This is what I would write if I wanted this. Most times I see this mistake made something like if you see this inverse tan, right? Like for example, inverse tan. And we'll talk about this in another video. Inverse tan, as you remember, it's like the arc tan. It's the arc whose tangent is x, right? It's not 1 over tan. 1 over tan, it's cotangent. Okay, so just don't make this mistake. If you see that -1, they mean inverse.